Epilepsy, characterized by recurrent, unprovoked seizures, is often viewed through the lens of abnormal electrical activity in the brain. But beneath these electrical storms lies a crucial biochemical reality. Seizures are energetically expensive. The brain, during a seizure, demands vast amounts of fuel, far more than in its resting state. This acute energy requirement raises the question of how neurons and glial cells meet such surges in demand. One underexplored but increasingly significant factor in this equation is glycogen, primarily stored in astrocytes as a rapidly mobilizable energy reserve. Could disturbances in glycogen storage or mobilization be more than just a background issue in epilepsy? Could energy mismanagement, especially involving glycogen, be a trigger or amplifier for seizure activity? In the healthy brain, glycogen acts as a buffer for short-term energy crises. Stored in astrocytes, it can be broken down into glucose, 6-phosphate, and further metabolized into lactate, which is shuttled to neurons during periods of high demand. This astrocyte neuron lactate shuttle is crucial during intensive cognitive effort, prolonged wakefulness, or localized energy shortages. In the context of epilepsy, where sudden and extreme spikes in activity occur, this reserve would seem to play a protective role, helping neurons meet their heightened metabolic needs without falling into energy failure. However, studies in both animal models and epileptic human tissue suggest that this system may be disrupted in epilepsy. Some brains show abnormal glycogen accumulation in regions prone to seizure initiation, such as the hippocampus. Others reveal signs of impaired glycogenolysis, the process of breaking down glycogen to usable energy, potentially leaving neurons vulnerable to fuel shortages during seizures. This scenario, in which glycogen is either unavailable or inefficiently mobilized at a critical moment, could contribute to seizure propagation or even act as a primary trigger. One hypothesis is that a failure in astrocytic glycogen metabolism may precede the electrical instability observed in epileptic foci. During interictal, between seizures, periods, low-level hyperactivity and inflammation could gradually deplete glycogen stores or impair their replenishment. When a seizure begins, the sudden need for energy may outstrip the available supply, leading to local metabolic collapse and further exacerbating the seizure itself. This feedback loop, energy deficit fueling electrical chaos, could help explain why seizures often arise in metabolically compromised regions of the brain. Conversely, excessive or poorly regulated glycogen accumulation may also be problematic. In some forms of epilepsy, particularly those with genetic or metabolic origins, aberrant glycogen storage has been observed. These forms of glycogen, often less branched and more resistant to degradation, may interfere with astrocyte function, disrupt neurotransmitter clearance, and promote neuroinflammation, all factors known to increase seizure susceptibility. This has been most clearly demonstrated in Lafora disease, a rare and severe form of progressive myoclonic epilepsy characterized by the buildup of insoluble glycogen-like structures known as Lafora bodies. These toxic aggregates not only impair energy metabolism but actively contribute to neurodegeneration and seizure activity. Importantly, this metabolic dimension of epilepsy opens potential avenues for new therapeutic strategies. If glycogen dysregulation plays a role in seizure generation or severity, then modulating this pathway could be beneficial. For instance, enhancing glycogen turnover or improving lactate shuttling through pharmacological agents might help stabilize energy availability during early seizure phases. Some experimental treatments already aim to target astrocyte metabolism as a way to influence neuronal excitability indirectly. Dietary approaches, particularly ketogenic diets, also tie into this conversation. By shifting the brain's primary fuel source from glucose to ketones, these diets may reduce reliance on astrocytic glycogen and mitigate the impact of its dysregulation. Interestingly, one proposed mechanism for the efficacy of ketogenic diets in epilepsy is their ability to stabilize glial neuronal energy dynamics and reduce the likelihood of energy failure during electrical stress. This suggests that the benefits of such diets may extend beyond their known effects on neurotransmitters and ion channels, reaching deep into the brain's metabolic infrastructure. Still, caution is warranted. Glycogen is a dynamic molecule, and its regulation is influenced by numerous factors: sleep patterns, hormonal signaling, inflammation, and neuronal activity itself. Interventions that disrupt glycogen metabolism indiscriminately could have unintended consequences, such as impairing cognitive function or resilience to other forms of stress. Understanding the context-specific role of glycogen in different seizure types, brain regions, and patient populations will be critical before translating these findings into clinical practice. In conclusion, glycogen's role in epilepsy is neither peripheral nor passive. As the brain's emergency energy reserve, it may act as both a buffer against and a contributor to seizure activity, depending on how it is managed. The evidence increasingly points to glycogen mismanagement, not simply glucose deficiency, as a possible factor in seizure generation and maintenance. If this proves true, then future therapies may not only aim to control electrical storms, but also to stabilize the metabolic landscape that makes those storms possible. In this view, epilepsy becomes not just an electrical disorder, but a metabolic one, and glycogen may be one of its hidden gatekeepers.